Okay, now we're going to detailedly discuss the theorems in the module 1. Okay, so the theorem here is that if a graph has exactly two vertices v1 and v2 of odd degree, then there must be a path joining to v1 to v2. This is that question. That is, it said that if a graph has exactly two vertices, in a graph there are two vertices v1 and v2 which is of odd degree, then we have to prove that graph, if there is only two vertices of odd degree, then there can be a path exists between v1 and v2. So I'm going to ask you one question: how would a path exist? When is a path going to exist? That is my first question. When is a path going to exist? A path can exist only when this v1 and v2 are in the same component, right? In the same component, only then a path can exist between them. That is what we have learned in the previous videos where we have discussed our theory part, right? So if this this graph can be connected graph also, it can be disconnected graph also. So we need to know that if only two vertices in this whole graph has odd degree, then those two odd degree vertices must lie in the same connected component, so a path can exist between them. Only if these two vertices is present in the same connected graph, then only there can be connected graph, disconnected graph. If they are present in the same connected graph, then only there can be, in the connected graph only a path can exist, right? So only if this v1 and v2 is present in the same connected graph, then only a path can exist between them. So we know from our theorem, the first theorem that we have learned, that is known as our handshaking lemma, that we have learned in the previous video. This theorem proved that the proof was that the sum of degree of all vertex is 2 times the number of edges. This was our proof that we have proved. So the sum of degree is always even. So in the second proof that we have learned in the previous video itself, we have learned already one. After proving this, we have learned another proof that, so the sum of the degree of odd vertices, that is sum of vertices with odd degree, would also be even. This is what we have learned. So we need this basic concept to understand this problem. So we know a path can exist between this v1 and v2. Like a path would exist between when there is an edge between them, or some one or two edges would be between this v1 and v2. So that means this v1 and v2 should be a connected graph, should be present in a connected graph. Then only this v1 and v2 a path can exist. So we have to prove this. How can we prove this, right? For that, first we took the help of our handshaking lemma. We know the sum of degree of all vertices is 2 times the number of edges, which we have already proved. So from that theorem, we have already proved that if this is the condition, then the number of odd degree vertices in any graph should be what? Even. So let us say that, suppose we have a graph G, and let us say that we have two odd vertices. So the graph has two conditions. The graph is connected. If the graph is connected, we know the connected graph, there are two cases we have to consider. The first case is that the graph is connected. Okay, if the graph is connected, there would be exactly one path. There would be exactly, at least there should be one path between every pair of vertex. That is the definition of connected graph. So if every pair of vertex has a path between them, if that is the definition of the connected graph, then v1 and v2 there would be a path between them. Hence, if the graph is connected, we can say that v1 and v2 would have a path between them. Now the next thing comes, so that means hence the theorem can be true. But the next thing is that what would happen if the graph is disconnected? If a graph is disconnected, then if graph is disconnected, then you can split this graph into, let's say, two components. That is two components we can split. So we know each of these components would act as a graph. That also we know, right? So that means each of these components can act as a graph. So we know in a graph, if I'm considering, each of these components can act as a graph, and we know in a graph there can be only if there is odd vertex in it, then the odd vertex should be always an even number. That is what we know from handshaking lemma. If we have odd degree vertex, that should be an even number. So that means in this graph, the number of odd degree vertex can be either 0, no odd degree vertex, or then it can have 2 odd degree vertex, 4 odd degree, like that. It should be even. Like that, in G2, that is another disconnected component, if we have a odd degree vertex, it can be in 0, 2, 4 numbers, right? Even number. And in the question which is given that only 2 of the V1 and V2, only 2 odd degree vertex is there. So if there is only 2 odd degree vertices there, then the 2 of them should be present in G1 or G2. That is, we cannot say that in G1 there would be 1 vertex and in G2 there would be 1 vertex. How we cannot say that, because we know in G1 there should be even number of odd degree vertex, but if only V1 if I am putting in G1, then that means what? That means this one vertex of odd degree is only present in G1, but that cannot be the condition, because according to handshaking lemma, the number of odd degree vertex in a graph would be what? Even. So in G1 there should be even number, G2 there should be even number. So we have to conclude that V1 and V2 together should be in any one of the component, right, if the graph is disconnected. So if it is present in any one of the component, then we can say that there would be a path existing, because it is a connected, a graph, if you can say a component is a connected, one component if you take that is connected. So that means there would be a path between V1 and V2, right? So that is how we are proving here. So each component can have 0, 2, 4 and all, but never one odd vertex. So the graph if the graph has only V1 and V2, so the total number of odd vertices is 2. So imagine V1 is in one component and V2 is in another component. Then component containing V1 has only one odd vertex and component containing V2 has only one odd vertex. This is impossible, because in each of the component there should be even number of odd vertex. So that cannot be possible. Therefore we can say both this odd vertices should belong to the same component. If they are belonging to the same component, there would be a path between them. So then we can conclude. Hence our theorem is proved. So how we are proving this theorem? If it has to be, if the two vertex V1 and V2, if there should be a path, odd degree vertex, if there should be a path existing between them, then we say that it should be present in a connected graph. Let's imagine that let's consider G with V1 and V2 vertex, which is odd degree. Let us say that the G can be a graph G is connected. If the graph is G is connected, we know by the connected graph definition, every vertex there would be a path existing between every vertices. Every pair of vertices has a path between them, right? So therefore V1 and V2 would have a path. Now if let's say the G is disconnected, then you can have component 1, component 3, like that. Lot of components are possible, but we know by handshaking lemma, that is a number of odd degree vertex is always even. So in each of the component each of the component can be treated as a graph. So each of these component graph can have only the odd degree vertex should be always even. So it can be 0 odd degree vertex, 2 odd degree vertex, 4 odd degree vertex, etc. It will go on like that. So if you have only 2 odd degree vertex, then the 2 odd degree vertex should be present in one component itself. If you are putting V1 in one component, V2 in another component, the component with V1 would have only one odd degree vertex, and the component with V2 would have only one odd degree vertex, which is not possible. So therefore V1 and V2 should be present in one of the component itself. So this is how we are proving this theorem. Okay, fine. Now let's see how we are proving this. This is what this proof is important for developing the next theorem. So that is why we have to learn this proof. The proof is that maximum number of edges in a simple graph is n into n minus 1 by 2. So we have to learn to prove this. Then only we will be able to learn this theorem. Which theorem? Then only we will be able to learn this theorem, and this is one of the most important theorem of module 1. So if you wanted to learn this theorem, then we have to know how we are going to prove the maximum number of edges question. So a simple graph with n vertex has at most n into n minus 1 by 2 edges. This is a proof theorem that we are going to prove right now. So in a simple graph, if there is n vertex, the number of at most how many edges can be possible? N into n minus 1 by 2. That means simple graph means there is no proof, no parallel edges. Alright, that is the condition. So here a vertex cannot connect to itself, right? So each vertex, so if you consider a maximum degree of each vertex, a vertex is not connecting to itself because we are not considering self flow. So each vertex can connect to at most the other n minus 1 vertex. At most we are talking about at most. So at most means one vertex can connect to other all vertex. That is, if there are n vertex, so one vertex can connect to all. If let's say 4 vertex are there in total. So if I'm taking the first vertex, let us say v1, at most v1 can connect to v2, v3, v4, right? But v1, we are not considering self loop because we are considering symbol graph. So in symbol graph, v1 cannot be connected. v1 cannot be connected to itself, no self loop. So maximum v1 can, if there are 4 vertex, v1 can connect to v2, v3, v4. That is 3 vertexes it can maximum connect. So that means if I have n vertex, so one vertex can connect maximum to what? N minus 1 vertices, right? If there is 4, if it can connect to maximum 3 vertex, if I have n vertices, then one vertex can connect to maximum how many vertices? N minus 1 vertices, right? So maximum degree possible for this vertex would be what? 1, 2, 3, 3. So that means maximum degree possible would be what? We are talking about maximum condition, okay? So maximum degree possible would be what? N minus 1. So we know from handshaking lemma, we know the sum of the degree is what? The sum of degree for n vertex, if you consider, it is n minus 1 plus n for each of the vertex. If you take the maximum degree to be n minus 1, and if you have n vertex, then n minus 1 you have to add n times. So if you have n vertex, the sum of all degree would be what? N into n minus 1. For each maximum degree is n minus 1. So for n vertices, it would be n into n minus 1. And we know by handshaking lemma, this is the sum of the degrees 2 times of number of edges. So we can substitute here 2e to be equal to n into n minus 1. So edges would be what? N into n minus 1 by 2. Okay. So this is how we are applying handshaking lemma here. So if you have a symbol graph with n vertices, then you can say one vertex can connect to at most n minus 1 vertices. So the maximum degree possible for one vertex would be what? N minus 1. So we know if I am finding summation of degree of all the vertex, it is n into n minus 1. For one vertex it is n minus 1. So for n vertex it would be what? N into n minus 1. So in the handshaking lemma, we are putting this LHS here is equal to 2e. So e is equal to n into n minus 1 by 2. Okay.